Hello and welcome. My name is Brian Rodriguez, and I'm a professor in the School of Physics at University College Dublin. Today, I'd like to introduce you to a technique that we use in my research group called Atomic Force Microscopy, starting with the basics. Now, this isn't an AFM. It's the stylus of a record player and the grooves in a vinyl record, but we can use it to illustrate some basic principles of AFM. AFM is something like a touching microscope, where a tip at the end of a cantilever is used to feel the interaction forces between the tip and a surface in order to make a picture of the surface. Here are several commercial AFMs. You can see they come in various configurations. They can image large samples, be combined with optical techniques, and be used to image samples in air or liquid with up to atomic scale resolution. And our main objective for this lecture is to understand how we can obtain images from an AFM. How do we go from the AFM itself to a 3D map of a surface like collagen shown here? So what are the main components? As you can see, we need an AFM probe and a sample. The probe is usually made of silicon or silicon nitride and has a cantilever with a sharp AFM tip at the end. Now, if we just bring the tip and sample together, we have a problem. The probe breaks. We need to know when to stop the approach. We need to do this in a controlled fashion, because what we want to do after approaching is drag the tip along the surface and have it trace out the features of the surface. So how do we do this? An easy way to think about what we are measuring is the displacement of the tip through the bending of the cantilever. But how can we measure this? By far the most common approach is called the optical beam deflection method, where a laser is reflected off the backside of a cantilever into a position-sensitive photodetector. Here we can see the basic design of an AFM. We have a laser focused on the backside of a lever, reflected into a photodetector with a mirror, and then we can move the tip or sample to trace out an image of the surface. But what is a photodiode? A photodiode converts light to voltage. So as we move the laser onto the photodiode, we start to see some signal. We can split the diode, and we can see that we get 1 volt from the top half and 1 volt total. We can zero the difference between the top and the bottom by placing the laser in the center. And if we have 4 quadrants, we can center the spot left to right as well. This is something you do, or the AFM does automatically at the start of every experiment. Why 4 segments? Well, AFM can be used to measure friction and torsional forces as well. How is the force calculated? Well, we treat the lever like a spring and apply Hooke's law, where delta Z is the tip displacement and K is the spring constant. But that's not all. We need other components too, particularly motors and scanners to move things in some way to control the system. Much of this was already developed in the original AFM, first reported in 1986 and built on the back of the Nobel Prize-winning scanning tunneling microscope. You can see the original AFM in London's Science Museum. Now we're getting somewhere. Here's a full schematic. We can see our probe and sample, our optical beam deflection method, some way to position the tip, a computer for recording the images, some way to move the sample. Here you can see an XYZ piezo tube scanner, and here you can see an XY piezo stack sample scanner. Quite importantly, there's a feedback system. This is at the heart of AFM. It uses the detector signal to make adjustments in the tip sample separation. The most straightforward mode of AFM operation is contact mode. This will help us understand the feedback loop better. In contact mode AFM, you choose an operating set point. This sets the force you will image at. This is called constant force mode. The force is 0 when you align the laser and 0 the deflection. When you approach, the cantilever is lowered until the set point is reached, in this case, 1 volt. So what is this feedback method? An electronic device called a controller is used. It continuously compares the chosen set point with the deflection signal measured. The difference between the two is the error, and this error signal is used to determine the appropriate voltage to apply to adjust the tip sample separation. A parameter called gain is used to control how sensitive the system is, how quickly it responds. These animations really highlight the role of the feedback loop. On the left, feedback is disabled and constant height mode is used. Obviously, for samples with sufficient height variations, this won't work. On the right, we can see the constant force mode with feedback enabled. The tip sample separation is adjusted proportionally to the cantilever deflection. As you can imagine, the set point or force applied, the scan speed or tip velocity, and the feedback gain are all important parameters. Here you can see a trace and retrace of a raster scan. The tip moves right to left and then left to right. The two lines should match up. And when they don't, It's a sign that the scan parameters need to be adjusted. Choice of tip is also critically important. The shape and aspect ratio can be important considerations. As shown here, a sharp tip accurately follows a surface compared to a blunt tip. This is a type of tip convolution or tip imaging, and is something you have to be careful with when collecting data. Sometimes your tip will break into a double tip, or you will pick up contamination on your tip. All of the surface features will now look like your double tip or your contamination. An important application of AFM is force spectroscopy, or measuring force distance curves. These can be used in a variety of different types of measurements, from measuring the modulus of a sample to the adhesion of a sample to the forces required to mechanically denature a protein or break a ligand-receptor interaction. Shown here is one such force distance curve. We start at A, far from the surface, and approach the surface. At B, we have snap to contact. The tip is attracted to the surface. The attractive force gradient was greater than the spring constant in this case. Then along C, we are pushing into the surface with a tip. Then along D, we are retracting from the surface. As we pull away, the surface holds on to the tip until at E, it is released, and then we arrive back at F, far from the surface with no force. In air, this adhesion is due to the capillary effect. Surface water is essentially holding on to the tip as we try to retract. But where are we getting force from? Before, we were only talking about a photodiode voltage. So we need to consider calibration in two stages. First, we need to relate the photodiode voltage, the cantilever deflection in volts, to a cantilever deflection in nanometers. To do this, we do a force curve on a hard surface, where we move the tip a known distance and measure the deflection in volts. This volts to distance comparison gives us what is known as the inverse optical lever sensitivity, or invols, typically in nanometers per volt. Now that we have the deflection in nanometers, we recall that we determined force from Hooke's law, so we need to figure out the spring constant. With K and delta Z, we can then calculate force. K can be determined using the so-called thermal method. We just record the vibrations of the lever at all frequencies using the photodetector. These thermal fluctuations due to Brownian motion, to molecules interacting with the lever, cause the lever to vibrate more at its mechanical resonance. So we measure the noise, use the invols to convert the noise in volts to noise in nanometers. We perform a simple harmonic oscillator fit of this thermal peak to extract parameters, and we apply the equipartition theorem, which just states that the energy associated with the vibrations is equal to 1/2 kBt, allowing us to solve for the spring constant. There's also a non-invasive way, meaning no force curve required, to obtain both invols and K from the thermal, called the Sater method. So far, we've been talking about contact mode. In contact mode, you're always applying a force, but you're also scanning with this force. So there's also the torsional force. This can be problematic for soft and loosely attached samples. Dynamic AFM, or commonly called tapping mode, overcomes this problem. I like to refer to it as amplitude modulation mode, but it comes under different names. Whereas the thermal noise measurement was just recording the natural state of the lever, now we want to drive the lever vibrations. We do this most commonly using a piezoelectric element close to the probe. When we apply an AC signal to the probe, the lever and tip oscillate at the same frequency. As shown here, you can see the AC voltage to the piezo, and the resulting AC signal in the photodetector corresponding to the lever oscillation. Like with contact mode, we will use a feedback loop, this time to keep the amplitude constant. So what do we mean by amplitude? AFMs make use of a lock-in amplifier to separate the response at the drive frequency from the full photodetector signal by comparing the drive as the reference with the raw signal. This yields the amplitude and phase of the oscillation. We'll talk about phase later. For amplitude modulation mode, we need to consider the interaction forces. In contact mode, we are operating entirely in the repulsive regime. An easy way to do this is think of our lever as a spring. As the tip gets close to the surface, the resonance of this lever spring will change. The long-range attractive forces will act to pull the tip to the surface, the spring will elongate, and the resonance frequency will decrease. As we get closer, the short-range repulsive forces will push the tip away from the surface, compressing the spring, and the resonance frequency will increase. These shifts are shown visually here. Generally, you want to operate in the repulsor regime to get nice images in amplitude modulation mode. So as we've been discussing, as the oscillating probe approaches the surface, there will be an interaction force that causes a frequency shift. In amplitude modulation, we stay at a particular AC voltage frequency. And so when the cantilever frequency shifts, there will be a change in amplitude at our drive frequency. We will use this change, typically a reduction in amplitude, to determine our set point for imaging. If the amplitude is reduced significantly, the set point is small. And if the amplitude is reduced only slightly, the set point is large. It's very close to the free amplitude. This is shown nicely here. It's like an amplitude versus distance curve. We start far from the surface with our free amplitude. As we start approaching the surface, it stays the same until we start interacting with the surface, and then it reduces. The amplitude will decrease. We might choose a set point or amplitude reduction here to do our imaging. If we happen to keep going closer and closer to the surface, our amplitude will continue to decrease. That gives us the basic operating principles of amplitude modulation mode. For comparison, we can see side by side contact and amplitude modulation or intermittent contact mode. Both use a feedback loop in the same way to adjust the tip sample separation to maintain the set point. In contact mode, the deflection is kept constant, and in amplitude modulation mode, the oscillation amplitude is kept constant. Earlier, I mentioned phase, so let's revisit that. What happens when the tip taps the surface? Something different must happen if the sample is hard or soft. This can be apparent in the phase signal, the phase shift or lag between the drive, the AC voltage we send, and the response that we measure. The tip will bounce back immediately from a hard surface, but lose energy in tapping a soft surface. While it would be nice to just attribute it to hard versus soft, it can be more accurately described by energy dissipation in the tip sample contact, and it can relate to elasticity, but also surface chemistry and topography. I think this is only the second AFM image in the lecture, which now seems a bit strange, but on the left, you can see an AFM image of 3 bacteria. Phase images often give interesting features and show otherwise hidden information. The phase image on the right reveals what's under the forming biofilm. So far in this lecture, we're barely tapping the surface of how AFM works. There are many other considerations and applications. For instance, your choice of probe. Maybe you want to do electrical or magnetic measurements, or you want to functionalize your probe, or use diamond to reduce tip wear. Shown on the bottom are spherical probes for mechanical measurements and functionalized probes for high-resolution imaging. As I come to a close, I just want to highlight some of the many applications of AFM. Here, mostly as it relates to biomedical applications, a wide range of measurements are possible, from imaging surfaces, particles, cells, to doing mechanical measurements, and measuring what happens at solid-liquid interfaces, key to many biological processes. And lastly, here are a couple highlights showing some impressive applications of AFM. Nanomechanical mapping of a live cell. You can see height on the left and modulus on the right. High-speed and high-resolution imaging of motor protein myosin walking along actin filaments, a kind of super resolution imaging of an X and V, a phospholipid binding protein, and CRISPR-associated protein 9, Cas9, an enzyme that cuts DNA. Hopefully with this lecture, you've learned the basics of AFM. Thanks for your attention.